Okay, good morning, everybody. So I believe that during these 3 lectures, I told you about, I would say, most complicated parts of this lecture course. Perhaps I didn't go as far as I wanted to. It was slow. And what I'm going to do during the last lectures, I will discuss a few mechanisms for baryogenesis. Okay. I should say that about some 10 or 15 years ago, I managed to count the number of mechanisms for baryogenesis which were invented at that time, and I found that there were 42. So I expect that if we count this number today, we will get an even larger number, maybe about 50, 60 different mechanisms for baryogenesis. Why so many? The answer is actually very, very simple. If you talk about baryon asymmetry of the universe, there is just one number to explain. And b over n gamma is some fraction 10 to the minus 10. And of course, the number of explanation is inversely proportional to the number which you have to explain. So the more numbers you have, the less explanation you get. So example is the standard model, for instance. Okay, so I'm not going to tell you about all possible mechanisms which were invented in the literature, and I will think that I will spend roughly half an hour for 3 different ideas which I find most interesting to myself. So one of them is electroweak baryogenesis. Electroweak baryogenesis on bubble walls. Okay, and this mechanism, it was invented by Andy Cohen and Nelson, and we learned about this strategy, which happened to her last weekend, and David Kaplan, her husband. So I will talk about this mechanism. Then I will talk about yet another mechanism, which is called thermal leptogenesis. And then the third one will be, which is called low-scale leptogenesis. And I will explain you what these different names are. Okay, so electroweak baryogenesis on bubble walls. Okay, so yesterday we learned that the standard model doesn't have phase transition, it doesn't have sources for making thermal non-equilibrium, which we need for baryogenesis. But perhaps, and most probably, the standard model is not the whole story, and perhaps the true electroweak theory at low scale does have an electroweak phase transition. Okay. How we can imagine this to happen? Okay, so if you have just a standard model, the Higgs potential is m square h diaga h plus lambda h diaga h square. Imagine that the Higgs sector is more complicated, and there are some extra fields. Okay, so it could be a singlet, doublet, a triplet, whatever. The particularly simple theory appears if you have extra singlet with the usual action 1/2 d mu high square 1/2 m square high square minus lambda high to the 4th, or minus psi h diaga h high square. Okay, so now you can take this theory or similar theory to that. You can use the machinery of finite temperature field theory, which you heard about from Guy Moore. You can compute the effective potential for the scalar field, and you can find out that yes, there is a choice of parameters in this theory in which the evolution of some combination of field H and I has the following form. So this is, say, H field, or some combination of H and I. This is high temperature potential. At very high temperatures we have this. Then the system cools down. You're getting another minimum. Then there is some particular temperature at which free energies of the system are the same. And then the potential involves in this form. Okay, and yeah, I show it. Like that. Okay, so this is the evolution of potential. Here T is greater than Tc, and here T is smaller than Tc. So what is going to happen in this system when the universe evolves? Okay, what is going to happen is that we are going to get a first-order phase transition. And how to deal with this first-order phase transition, you do the following. With the methods which are extremely similar to what I told you about with sphelerons, you can find a spheleron which is responsible for going over this barrier due to thermal fluctuation. Now, this spheleron is not called spheleron anymore. It's called the critical bubble. Okay. And this critical bubble it has the following structure. It's a spherical configuration, three-dimensional. So inside this configuration, the scalar field phi is not equal to 0. Outside this configuration, we are sitting in the symmetric phase. And this bubble is also spheleron in the following sense. If you squeeze a little bit this bubble, then it will collapse and disappear. If you make this bubble a little bit larger, it starts to expand, and it will fill out the whole universe. So it's literally a spheleron, but this type of spheleron people knew a long time ago when they were discussing first order superheated or supercooled phase transition in condensed matter physics. Okay? So it's a critical bubble. So how the phase transition occurs? You have you can compute the probability of that. Okay, you can compare it with the Hubble rate. You can find the time when this happens, and then the picture looks as follows. So you have initially the universe here in this state. It's trapped in this state. The universe cools down, and then there is spontaneous creation of different bubbles in different parts of the universe. Okay, so they are nucleated everywhere. Then they start to expand. Okay, and at some stage they collide with each other, and what is left behind is the universe in the new state. Okay, so that's the typical picture of first-order phase transition, and this is how it occurs in the early universe. Well, if the theory allows these transitions. Okay, so now how we can imagine creation of baryon asymmetry at this point, and that's exactly the work of Anne and collaborators, what they invented. Okay, so the picture is well, very nice and very transparent. So this is this bubble in which phi is not equal to 0 inside, okay? And outside, phi is equal to 0. Now imagine, yes?
So by phi you mean phi or?
Phi or Higgs or whatever, some scalar field, some other parameter which we introduce here, phi diagonal phi, so it doesn't matter. Yeah, I shouldn't contradict to what I was saying yesterday. So phi diagonal phi is small, and here phi diagonal phi is large. Okay?
And on the right axis in the potential plot?
Yeah, and this axis, so we put some other parameter. It's 5 diagonal phi, for instance. Okay. Okay, so now imagine that the phase transition is strongly first order. Okay. What do I mean? I have to quantify these words, strongly first order. So we want to produce baryons. Okay. But we want these baryons to survive till the present time. Okay. And if we want them to survive till the present time, here in this phase, these Faleron processes should be switched off. I'm not discussing yet the mechanism. Imagine that there is some mechanism which produces baryons. But if inside the bubble, Faleron are active and faster than the rate of universe expansion, whatever we produce, it will be destroyed. Okay? So, strongly first order phase transition means that inside the bubble, gamma Faleron over H should be smaller than 1. Okay, so if that were electroweak phase transition, forget that there is none. Perhaps the Higgs mass could be smaller than 126 GeV. Then that would mean that the temperature at which everything happens should be smaller than 130 GeV. Okay, remember this number. Yes.
But yesterday we found that it's. I mean, if we have only B plus L, it's gonna be washed out, as you pointed out. But if there is some initial B minus L, it would survive the.
Yeah. So I'm taking just the standard model and its simple extension, which doesn't introduce any new source for baryon number non-conservation. So the only source which we have for baryon number non-conservation here in electroweak baryogenesis through the main walls are Faleron. So there is nothing else. Okay, so if we start from 0 numbers, we can only produce B plus L. We cannot produce anything else. It was a good point. Okay. Yes.
I missed the role of and why we introduced this extra singlet in.
Yeah, because if you don't, then there is no phase transition.
Okay.
Yeah, you take the standard model. We know for sure there is no phase transition. Okay, so you have to modify something, since everything we are talking about restoration of symmetry, Higgs phase, symmetric phase. So we have to manipulate with scalars, and adding scalars indeed help. Okay, I can go through this point, but I think it was a job of Guy Moore. So I don't know if you've done that or not really. But to some extent, it's a straightforward thing. You take the formalism which he was describing, take the theory, compute the effective potential, and look at the form of this effective potential, and look at this picture. Okay, and if you find this picture, there is a first order phase transition. And not only that, you have to check that the transition is strongly first order, so you have to choose your parameters in such a way that the Falerons inside the bubbles are not active. Okay. Okay, so now about the mechanism. So we have plasma everywhere, okay, at high temperatures. And fermions, as you know, well, in the standard model, fermions are getting their masses from interaction with the Higgs field. Okay, and therefore, the masses of fermions, the standard model, or maybe some extension, are different in this phase and in that phase. Okay, so here we can say that fermion masses are large, and here outside fermion masses are small. Okay, and so and now you see what happens. This bubble expands. Okay, and the fermions, which are outside and inside, they are interacting with the main walls. Okay. So if you plot here, say, distance, and here we have mass of fermion, then inside the bubble, as I said, fermion mass is large, and outside is small, and here R is the radius of the bubble. Okay, so once you see this picture, you understand, of course, that the fermions will be scattered on these domain walls, and they can be transmitted or reflected. So if I take a fermion here, it comes to the main wall, there is some probability it will be reflected, but there is some probability that it will go through. Okay? Now, you remember that we need CP violation, and we imagine that there is CP violation in the theory. And what this CP violation can do for you, it can do the following. So this was for fermion, and now I plot the same for anti-fermion. And this is fermion bar. And I don't know if you see in this picture, I made this arrow and this arrow to be of the same length, but this arrow are different. So what I'm trying to show here is that the probability of reflection and transmission is in general different for fermions and anti-fermions. Okay? It may be very well, due to CP violation, it may be very well that the situation is the following, that fermions are mostly reflected from the main wall, and for fermions, that they are mostly pass through. Okay, so there is no any fermion number non-conservation in this process. This is just interaction of fermions with the bubble wall. Now, if this is indeed the case, what is going to happen is that when the domain wall moves, it separates baryon number and anti-baryon number. Okay, so what we are getting inside here, we are getting mostly baryons, and what we are getting here are mostly anti-baryons. Now we account for scleron transitions. So scleron transitions inside are doing nothing, because we have strongly first-order phase transition, and inside the sclerons are suppressed. Outside, we are in symmetric phase, and sclerons, what they do, they destroy the air anti-baryon number. Okay, and that's it. That's the mechanism. Okay, there is phase transition, bubble wall moves, there is separation of baryon and anti-baryon number. Outside disappears, inside survived.
So why is it that anti-fermions pass more, like have a higher probability to pass into the bubble than the fermions? And the other way around?
It could be another way around, yes.
It doesn't matter.
Well, it does matter in the sense that we know that we have baryons and not anti-baryons. But
yeah, so how can you ensure that?
Ensure you choose the parameters on the theory. Okay. Okay. So here we would be able to do that in the standard model to compute the sign. Okay. In the standard model, the only source of CP violation is Kobayashi-Mascava phase. We know what it is, and if there were bubbles in the standard model, then you would do a computation and find the sign. Okay, the CP violation is in any event so small that it wouldn't work. So here we are entering into the domain of BSM physics. Okay, we don't know what this physics is. We invent some model which has first order phase transition, and then in order to see what happens, you should study this model. Okay, and in particular, you may take this picture and compute this transmission and reflection coefficients. They will depend on other parameters, BSM parameters, and requiring that the sign is right, you would get some constraint on your preferred theory. Yes?
Is this also assuming the Spalon process, the gamma Spalon is different inside and outside the bubble?
Yeah, it's not an assumption, it's the fact of life. Okay. No, because here you are in one phase, here you are in another phase, right? And so we saw yesterday that in symmetric phase the sphelerons are fast, in the broken phase or in the Higgs phase they are suppressed. Okay, so the fact that they are fast here is automatic. There is nothing to do, okay, because you are in symmetric phase. The rate of spheleron transitions here outside is very high. I mean, you have to take care that the rate of spheleron transition inside the bubble is suppressed, okay, and this is associated with the strength of first order phase transition, and it's associated basically with the jump of the order parameter which you have when you go from this phase to that phase. So if this jump is small, the sphelerons inside are not necessarily suppressed, and then it won't work. Yes?
Can you remind me why fermion masses were important?
Sorry?
Why fermion masses were important for this mechanism?
Because of the following. We are considering interaction of these guys with the bubble, right? And if, for instance, the fermions do not interact with this field, they will not notice this domain wall. They just go through. And if it's like, imagine the following thing. Imagine that the fermion outside has an energy which is smaller than its mass in the Higgs phase. Then it cannot just go through. It will be completely reflected. Okay? Well, in reality, the situation is that the energies are thermal energies. They are greater than the masses, but this mass profile gives you the some potential on which the fermions scatter. Okay, so it's literally like in quantum mechanics. If you have 1 + 1 dimensional quantum mechanics, you have some potential of this sort. This is x, this is ux, and you look at particle. Okay, this particle will be scattered. It can go through. It can be reflected. It's 1-to-1 correspondence in this. So this is the idea. Yes.
So this domain is produced by the Higgs field.
Yeah, more general by scalars which exist in this theory. Yes, yes.
But in this particular scenario, is this domain produced by this chi field or this phi field?
Both of them, because they interact with each other, and so in this case, it's the structure of domain wall. It will be complicated, so it will involve two fields.
But this chi field, it doesn't have interactions with this fermion, right?
Yeah, it doesn't. Or if you introduce some other model, if it's a second Higgs doublet, that it will have interaction with the fermions. Okay, so these are kind of all details, really. The big picture is like this, and then you take your favorite model, you work out the structure of domain wall, you check this condition, you look at what interacts with the bubble wall, compute probabilities, etc. Yes?
So last lecture we said that it would teach temperatures bigger than 130 GeV, spallons are in equilibrium.
Yes.
So is this an extra constraint on this model that
Yeah. That's exactly this statement here. Well, 130 GeV, it was a number specific for the standard model. Okay, so if you go out of the standard model, these numbers are changing because you have more complicated picture.
Is
So
that number only valid in the symmetric phase? Because I'm thinking that if the temperature is low enough,
no, in symmetric phase, the rate of Swilleron transition is not suppressed at all. It's alpha to the 5th times temperature. So once you are in symmetric phase, you have thermal equilibrium. You have always equilibrium. In symmetric phase, always
so
equilibrium.
that number is only valid in the Higgs.
Yeah. Yes.
So inside the bubble, the Baryon rate is suppressed.
Yes.
But then how do you convert the lepton asymmetry to Baryon asymmetry?
No, here we produce just Baryon asymmetry. Because these guys are
You're
quarks.
talking about fermions or baryons?
Yeah, fermions is generic name for quarks and leptons together. Okay, so you produce B plus L. Okay, so you produce B and L asymmetry simultaneously. Inside stays, outside disappears.
So this is basically a model that can describe at the same time both baryogenesis and leptogenesis.
Yeah, if you want. Yeah.
What's the influence of the bubble dynamics?
The bubble dynamics is very essential for all this process. Okay, so that's a very good question. The things which are essential here are, for instance, the velocity of the bubble wall. Okay, why this is essential? Imagine that the bubble doesn't expand; it just stays like this. Okay, then nothing will be produced because we are in thermal equilibrium. We use one of the Sakharov conditions, and therefore the result should be proportional to velocity of the bubble wall. Okay. Now, suppose that the bubble moves very, very fast. So that's not very good from the point of view of this scenario. So why so? Because you create. Okay, here nothing happens. Here you have creation of some number of anti-baryons. And now there are two competing processes here. From one hand side, these anti-baryons want to be eaten by sphelerons. But if the bubble moves very fast, the sphelerons may not have time to do so, because this part of the space will be trapped in this phase because of the fast motion of the bubble. Okay, so indeed, the whole process, if you want to do real computation with accuracy within factor 2, is extremely far from being trivial. You have to understand the dynamics of the phase transition, what is the rate of bubble nucleation, what is the velocity of the bubble wall, whether the bubble wall dynamics corresponds to detonation or deflagration. So these are all things which are coming from different explosions. So here there could be different regimes on that. Then you have to take into account what happens with antifermions here. Not only sphelerons can be essential, but many other physical processes, scattering between them, etc. So this is kind of quite non-trivial, non-equilibrium statistical physics problem. Okay, and people worked really a lot on understanding different aspects of it, but the main idea boils down to that. Okay. More questions? Yes.
What's the amount of simulation needed to produce the standard model asymmetry?
Yeah, if you take standard model, then this is not enough.
Yeah, how much do you need?
You need to get 10 to the minus 10, and yesterday we saw that in the standard model you are 10 orders of magnitude
So
of.
it's linear in the
Yeah. So adding just the scalar to the standard model would be not enough. You need a new source of CP violation. So people worked, for instance, a lot on this mechanism and minimal supersymmetric standard model. Okay, and then the scattering of not only quarks were essential here, but scattering of other supersymmetric particles, gauge-genus, short-genus, etc., etc. So you have to plug in everything which you have in the model. Okay.
And what's the extra source of evaluation here?
Well, here, if you just add this, nothing. And so with this model, standard model, this stuff, it doesn't work because CP violation is not enough. So you have to add something else. Okay. There are many variants, and I don't want, since I said that I have half an hour for every mechanism. Yeah, maybe I will just write so a very, very rude estimate of the asymmetry, which you will get here. So this is a number of all degrees of freedom. Then you have here T minus T bar, and this T are transmission coefficients. Okay, so this is kind of factor which comes from particle physics. Okay, and here you need to have enough CP violation. And then there is some kinetic factor which depends on velocity of the bubble wall, which depends on the rate of Scaleron transition in the symmetric phase, which depends on different diffusion coefficient for quarks and other fermions. Okay. So this is associated with what I was talking to you here. If the main walls moves very fast, it can eat up the things which were not eaten yet by sphelerons. Okay. And so computation of this factor is relatively simple, because you just need to know the structure of the main wall, and then what you do, you solve quantum mechanical problem of fermion interaction with this domain wall, accounting for CP violation, which is in these reactions. So this is relatively straightforward quantum mechanical problem. To find this factor is complicated. And I'm not sure that people who are doing that, there are different groups, that they all agree with each other. Okay, so they're doing that in a different way. But getting results which are similar to each other, but not exactly the same. Okay, and the overall conclusion here that yes, one can invent BSM model in which this mechanism works. Okay, the consequence here is the following. You have to modify in some way electroweak phase transition. You have to have extra sources of CP violation, and since this is all electroweak physics, this should happen at not very high energies. It should happen with new particles or some new interactions, etc., in the 100 GeV TeV domain. Okay, so if indeed this mechanism was realized in nature, then the signal is that there should be some new physics beyond the standard model at sufficiently low energy scale. Okay. So these studies, phenomenological studies, they also have the following challenge. And actually, many, many models were rejected because of this type of consideration. Okay, so the logic is, I invent some model. Okay, I invent some model. I create Baryon asymmetry. Fine, and then I look at the electric dipole moment of neutron. Okay, I make a computation in the theory and find that it's bigger than that which we see experimentally. So it doesn't work. Okay, so there is a challenge. Since you introduce new physics here at relatively low energy scales, there are many phenomenological applications. There are CP violations appear in this and there where you don't want it to be. So the challenge is to make this go through, but at the same time be consistent with experimental data. Okay, this is possible, but this is challenging, and this may require different fine-tuning, some unusual choice of parameters, etc., etc. But the idea works. Okay, so I finished with this mechanism, and now go to something else. And here my discussion will be to some extent pretty much related to Graham's discussion yesterday. So I will go through quite a number of points faster, thanks to his lecture.
This mechanism should produce gravitational waves, right?
In principle, yes. Yeah, that's a good question. So once you have this bubble nucleation and bubble collisions, then you produce an isotropic energy stress in the early universe. And once you have an isotropic energy stress, that produces gravitational waves. Okay, and these gravitational waves, they have specific signature, they have specific frequency range, and in principle, they can be searched. Okay. So that's also people discussed quite a lot. Because there might be a connection here between baryogenesis and between gravitational waves, which may be discovered in the future.
If you don't mind the remark, there is a funny competition, because as you said, you don't want a too fast-moving bubble wall for a baryogenesis, but then for the gravitational wave signal, you really the force power of the bubble wall, so wall velocity.
Absolutely. So it may be very well that you get baryogenesis, but you don't get gravitational waves. This is perfectly true. Okay. So another approach to this problem, it comes from neutrino physics. And as Graham explained to you last time, neutrinos provide, at the moment, kind of the only indication that there is new physics beyond the standard model. Okay, there are neutrino masses which are not equal to 0. In the standard model, they are equal to 0. Different lepton numbers which are conserved in the standard model are not conserved in nature. So we know for sure that there is new physics here. Okay, and the question is what kind of new physics this could be. Okay, and I would think that the at least most minimal explanation of neutrino masses is the existence of right-handed neutrinos. Okay, and that's what also Graham discussed. I will denote these guys by letter N. Okay. So let's take the case which was also discussed yesterday, that there are 3 of them, N1, N2, N3. Okay. And now, using the principle that if we have new particles, okay, N1, N2, and 3, right-handed neutrinos, let's write most general Lagrangian generalizing thus the standard model. Okay, let's include all terms whatsoever we can write which are consistent with this symmetries. So Lagrangian will be Lagrangian of the standard model plus and bar I d n. So what kind of index I used here? Okay. Index I. This is just kinetic term. Okay, we can write also the Yukawa couplings. Let me write them like L F alpha I times L alpha bar times Ni times the Higgs field. Okay, so this is Yukawa coupling. This is left-handed doublet. These are our particles N, and this is the Higgs field. So this is the Yukawa coupling, which you would write for quarks as well. But since these particles are right-handed, okay, and they don't carry any SU2 cross SU1 cross SU3 charges, we can add here a term which is Majorana mass term, Mi over 2 Ni charge conjugated Ni, and then you add Hermitian conjugate. Okay, so this famous Lagrangian is called seesaw Lagrangian. Okay. For these particles N, there is kind of a name which you find in the particle data group. They are called HNL. And HNL is for heavy neutron lepton. Okay, and easy to remember this name. If you look at Yukawa coupling, you just see H and L. Okay. So this theory is very interesting. Okay, it could be the ultimate theory beyond the standard model. Okay, in the following sense, it can explain all neutrino masses, all neutrino physics. It can explain baryon asymmetry of the universe, and it can explain dark matter in the universe. Okay, and these are the three things which we, at least at the moment, tell us that there is new physics beyond the standard model. Okay, and so what I will going to do in the rest of the lecture, I will explain you how this model does all these things. Okay. So neutrino masses. So neutrino masses just require a few moments to talk about. This theory, in fact, it contains a lot of parameters. The number of parameters in comparison with the standard model is doubled. There are much more parameters here. There are parameters associated with Yukawa couplings here. And there are new parameters which are associated with the Majorana phase here. Okay, so I can tell you what do we have. So we have 6 new CP violating parameters. So in the standard model there was just one Kobayashi-Maskell matrix. But now there are a lot of CP violating phases sitting here which cannot be removed away because we have Majorana mass term. Okay, and then there are neutrino masses, and there are HNL masses, and there are a few new Yukawas. Okay, so we get about 20 new parameters in this theory. Unfortunately, in the standard model, we cannot predict yet, at least, any of these parameters of the standard model. So we are taking all of them from experiment. And this is true for this Lagrangian as well, this renormalizable Lagrangian, and the parameters which appear in renormalizable theory, they're taken from experiment. They cannot be computed. Okay, they're divergent, etc., etc. So what do we do with neutrino physics? So assume that this mass M is sufficiently large. And I don't tell you what sufficiently large is. I will tell you later. Okay, large would be meaning that M, which stands here, is larger than the Dirac mass Graham was talking about yesterday. And Dirac mass is F alpha I times vacuum expectation of the Higgs field, right? You put H here as a vacuum expectation of the Higgs field, and then you get another mass scale, which is F times H. So imagine that Mi is large, much larger than Dirac mass. So in this case, you can, so to say, integrate out these particles, and you can find what the mass of ordinary neutrinos would be. Okay. And if you do this exercise, this is an easy exercise which requires diagonalization of 2 by 2 matrix, roughly speaking. So the matrix you have here, M Dirac, M Majorana. This is neutrino, and this is N. Okay, so neutrino is 0 because they're all left. Neutrino N is Dirac mass because one is left, another is right. And Majorana mass is here because there is Majorana mass of neutrinos. Okay, so you analyze this matrix, you take into account flavor indices, and you find that the neutrino mass is equal to F alpha I, F beta I times V square divided by Mi, and here you have sum over I, okay, minus sign. So this gives you the mass matrix for ordinary neutrinos. Okay, and it is this mass matrix which is measured in different neutrino oscillations, and here you have in this theory enough parameters to fix this matrix to what is observed experimental. Okay. Okay, so important question for baryogenesis and also for the particle physics, or different particle physics experiments, is the question, what could be the masses of these particles? And unfortunately, from neutrino physics, we don't have any clue. So why so? The masses of neutrinos, we know. Okay, so the masses of neutrinos are of the order of, say, 0.05 electron volt. So we know what is this combination. We know what vacuum expectation value of the Higgs field is. And so we know the ratio of F over M. but we don't know F and M individually. If you say, well, this F should be like T-quark Yukawa coupling, then you say that, okay, this MA is a large number, 10 to the 11 GeV. Now, if you say, okay, well, these particles, they look like particles in the standard model. Why should their mass be larger than few GeV? Then you fix this mass, and then you find that the Yukawa couplings here should be of the order of few orders of magnitude smaller than the electron Yukawa coupling. Okay, so everything is possible. There is a huge parameter space in this theory, which fits perfectly with all experiments in neutrino physics, because they are blind to the absolute value of M. Okay, so go back to cosmology. What this theory tells us. Sorry?
This value, typical value of neutrino masses, 0.05 electron volt. This is a cosmological.
No. I'm just there is when you do measurements, there are different mass differences. Okay, so the mass differences which comes from atmospheric neutrinos is 0.05, 0.06 electron volt. Okay. And this number, it gives us the minimal value of neutrino masses. Okay, there are also upper bounds coming from cosmology, which are about 10 times larger. Okay, so I can write here 0.5 electron volt to be more safe. Okay, but this doesn't change the argument. Still, I mean, you have a huge variety of parameters which can give you the correct neutrino mass. Okay, so we are going to cosmology, and in particular for baryogenesis, leptogenesis, the thing to know is what are the numbers which are conserved in this theory. And now you see there is nothing conserved. Okay, so everything is broken. You have Majorana neutrino mass, which changes lepton number. So lepton number is violated. Yes.
So the question is, but here in the Yukawa coupling, you would get a term of the form Ni bar n, and in the Majorana mass, you would get the term of the form Ni complex conjugate bar n. So how can we write the mass matrix like this?
Sorry. What was the question? Can you repeat?
So here from Yukawa you would get Ni bar n, and from Majorana term you would get Ni complex conjugate bar n. That charge conjugate bar n. And so how can we group them together in this form?
You're talking about CISO formula.
Yes.
There was a plot written by Graham, but you do the following. X, left, and here is Majorana mass. Okay, so this is the CISO formula. Okay, so this point here is Majorana mass. It's exactly this form. Okay, and so if you look at Feynman rules, treating Mi as a perturbation, suppose we treat it as a perturbation, then the Feynman element here is like this or like that. Okay, so you have, since here you have NC bar conjugated, this is the same as N, and so you have arrows and different things. And that's the graphic representation of Majorana, of ordinary Majorana neutrino mass, which is written here. Okay, and it's important that I don't have here any F star. So this is literally F times F. Okay. Okay, so in this theory, lepton number is not conserved. Just because of the presence of Majorana mass, and because we have all these Yukawa couplings. Okay. On perturbative level, baryon number is not conserved, but there is anomaly, so baryon number is not conserved as well. So this is because of Majorana mass plus U-covers. And delta B is not conserved due to anomaly. Okay. So our discussion about Sphaleron erasure, which we had last time, is kind of not applicable to this model because everything is not conserved. Okay. So this is better than the standard model. As I said, we have 6 new CP violating phases. So this means that the arguments which we have computing different traces, which gave us 10 to the minus 20, is not applicable. Okay. And the last point was about thermal equilibrium. We had no thermal equilibrium. We had thermal equilibrium in the standard model. But here, it's an open question because we got new particles. And these new particles may behave in such a way that they go out of equilibrium in a different way, not like standard model quarks and leptons. Okay, so once we have that, it's kind of obvious that the life will be getting easier from the point of view of baryogenesis. Okay, so let's first look at the question of thermal equilibrium in this theory. So we got this extra entries, Majorana fermions. So let's see when this particle come in thermal equilibrium and go out of thermal equilibrium. I will be using the following formula. Mass of neutrino is of the order of F square V square over N, just for estimates. Okay, in principle, there is a rich flavor structure here. There are indices corresponding to different fermionic generations. But just for an estimate to get feelings of the numbers, let's just assume that all masses are of the same order and all U-covers are of the same order, just to get some numbers. Okay, so we have this relationship. So that gives us an estimate of U-cover coupling, which is m nu times mn divided by width of the Higgs field square. And for estimates, I will be taking mu 0.005 electron volts. And we know V is 250 GeV. Okay, now we ask ourselves, what are the most rapid process with HNLs, with heavy neutrinos. So the diagram which we can write looks like that. Higgs TT bar. Okay, N nu H is coming from this Yukawa coupling. So they can collide, create H, and H is coupled most to top quark. Okay. So this the rate of this process should be of the order of okay, there is some factor 10 to the minus 2, phase volume, stuff like that, times Yukawa square times temperature. And I forget about top quark Yukawa because it's 1. Okay, so this is the rate of HNL interactions, and we can compare it with the rate of universe expansion, which is T squared over M0. So you put here the numbers, and you find that this rate is greater than the rate of universe expansion for temperature greater than about 30 mass of Mn. And I'm taking Mn as a free parameter. Okay? So this is the estimate of freezing temperature. Yes. So freeze out temperature, as usual, as in the example which we discussed during the first lecture, is estimated in the following way. In order to get freeze out, we have to take into account that the concentration of these particles, if the temperature is smaller than its mass, is behaving as exponential minus m over t. So when the temperature gets smaller than the mass of these particles, their rates are suppressed by that, the inverse rate. Okay, and this leads to a conclusion that T freeze out is some number, but in any event, this is smaller than the mass of this particle. Okay, so we can make a plot. This is temperature. This is gamma over h. This is 1. And we have something like this. Yes?
Why is n not decaying very fast? Capital N.
Yes.
If its mass is greater than 2 top, then it can decay to neutrino and Higgs.
Yeah. Well, immediately, the words immediately doesn't sound right. It decays with some rate.
It decays with some rate, but
Yeah.
wouldn't that be even faster than when it's freezing n?
The answer is no. Okay. And the answer is no because of the following reason. Adding this vertex, it doesn't change anything because Yukawa top is equal to 1. So you can remove this and you will still get the same estimate for certain.
So it would be the same estimate?
Yeah, it is the same estimate. Yeah, so this process you are talking about should be taken into account, but it doesn't change any estimates of which I'm doing.
So you're saying, like, once it goes to thermal equilibrium, then like
Yeah, okay, if you consider decay of n into this thing, if t is smaller than mn, then the rate of this process, gamma, it will be of the order of Yukawa square times mass of n. Okay? And here I was discussing the case where temperature is larger than mn. And so this process of decay will be less fast than this one. Okay? And decay of, say inverse decay of that, it falls into another category which is associated with freeze-out temperature. Okay. Yes, in order to see in more detail what's happening, you have to take into account all possible processes, look at their rates, compare these rates with the rate of universe expansion, but you will get roughly within factor of u this picture. So this is temperature T star. This is temperature T double star. And this temperature T star is fraction of mass. And this guy here is roughly 30 mn. Okay, maybe it's not 30, maybe it's 50, 60, but it's not important for us at the moment. Okay, so now this is a picture in which we have the history of our new particles, HNLs. Our new particles, HNLs, they interact with the leptons. They don't interact with quarks, okay? Because their quantum numbers are such that they can only interact with leptons. And they have different CP violating phases in interacting with leptons. Therefore, whatever mechanism you invent for which leads to asymmetry, that would be lepton asymmetry. And we are interested in baryon asymmetry. Therefore, we have to combine two considerations. One consideration is associated with equilibrium or non-equilibrium characters of HNLs, and another consideration is associated with Feleron non-conservation, which potentially can allow us to transform lepton asymmetry into baryon asymmetry. And that we already know. We can also have here gamma Feleron over H. This is 1. And here we have the similar plot. This temperature is about 10 to the 12 GeV. And this temperature here is 130 GeV. Okay, just one remark. In this theory, if you talk about electroweak phase transition, Feleron rate, etc., there are no changes in comparison with the standard model. So it's absolutely the same. In the standard model, no phase transition. Here, there is no phase transition. So this HNL, they don't do anything. Okay. The rate of Feleron transitions is also immune to these particles because they're right-handed. They don't participate in this Feleron reaction. So all these pictures for Felerons are taken from the standard model. So during this time, conversion of lepton number to baryon number is possible. Outside this region, this is not possible. Okay, now consideration of that allow us to have two logical possibilities.
But can I ask? So you said before that since there are no symmetries here, the Feleron don't play any role.
No, I didn't say that.
I understood.
No, Felerons, of course, must play a role, because if you forget about Felerons, then this theory would only produce a lepton asymmetry, and that's fine, but we need baryon asymmetry. No, Felerons are absolutely crucial here. Okay, so we get two logical possibilities. So the first possibility is in which mass of n is greater than Feleron temperature, which is 130 GeV. So if this is the case, then n go out of thermal equilibrium at t greater than t spheron. Okay, so if we consider overlap this picture here, then the first possibility is when this point, t star, is somewhere in this region. Okay, and so if this is indeed the case, then we may expect to have generation of lepton asymmetry at temperature T star. And since sphelerons are active here, this lepton asymmetry will be transferred into baryon asymmetry. Okay, so they go out of, and this mechanism is called thermal leptogenesis. And that was invented by Fukuhita and Yanagida. In 86. And then there is a second possibility in which mass of n is smaller than t spheron. Okay, and this means that we are taking this picture and we are shifting it in this region, and this means that the production of baryon asymmetry should take place at the temperature T double star, because T star is in this domain where sphelerons are not active, and therefore conversion of lepton asymmetry to baryon asymmetry is not possible. And this is called low-scale leptogenesis. And this mechanism was invented by Akhmedov, Rubakov, and Smirnov. In 98, and then we made some important contributions together with Asaka in 2005 into this consideration. So what I'm going to do in the last 15 minutes, I will tell you the basic ideas of how these two mechanisms work. Okay. So let's start from thermal leptogenesis. So I'll keep these pictures here. So what happens in thermal leptogenesis? We have the universe, high temperatures. At temperature T double star, our particles enter in thermal equilibrium, and then at temperature which is fraction of mass, they decouple. So during this period, they come in thermal equilibrium, and so their concentrations are equal to thermal equilibrium concentrations. And at T star, these particles decay. So how do these particles decay? N can decay into H lepton and say, okay, H plus lepton minus, H minus L plus, H0 anti-neutrino, H0 bar neutrino, and these are the main channels of this decay. Okay, so this is a Majorano particle. It can decay in this channel and in charge conjugated channel simultaneously. Since we have CP violation, Small h is, this is charged Higgs, this is neutral Higgs. So Higgs is the Higgs doublet. Okay, we are temperatures which are above electroweak crossover. So H is kind of a true particle there. And in the Higgs doublet, there is neutral component and there is charge component. So I put them separately. So CP non-conservation. Means that the width of n to the channels which correspond to lepton is not equal to the width which corresponds to anti-lepton. Okay. How do you see that? This is the straightforward computation, okay, which I'm not going to describe, but it boils down to a computation of the following graphs. So this is a decay in tree approximation. In tree approximation, you don't see CP violating effects because you take a modular of the amplitude and all CP phases are going away. But what you should do, you should add to that loop diagrams. Okay, there is this type of loop diagram in which you have insertion into H&L leg of a Higgs loop. And then there are triangular graphs of the following type. So this is Higgs, this is lepton, this is N. And you put here all this Yukawa couplings. Okay, so what you do, you make this computation, make a square of the amplitude, and then you find out that gamma L is not equal to gamma L bar. And so we are coming to original Sakharov idea, where he said that we have some heavy particle, this heavy particle decays, and during its decay, it have a remnant, and in this case, the remnant will be lepton asymmetry. Okay. So what is the final result of the computation? And the final result of the computation is the following. Oops. So Harvey, sorry, I broken the microphone. Thank you very much. I don't know. Well, I can keep it in hands. You think it goes this way? Yeah, let me see. No. Okay, I'll try it. Okay, so let me try it this way. Okay, so the final result for lepton asymmetry will be of the order of 1 over total number of degrees of freedom. Then the asymmetry in gammas, gamma L minus gamma anti-L, gamma L plus gamma anti-L. So that's what we can compute by doing thermal diagrams. And then there is the non-equilibrium statistical factor. And this non-equilibrium statistical factor accounts for thermal equilibrium or thermal non-equilibrium. It accounts what whether the process of decay of this particle occurs in thermal equilibrium or it occurs out of thermal equilibrium. Okay. So the
So what is the 1 over large n?
sorry? Yeah, sorry. This is total number of degrees of freedom. So n effective is total number of massless degrees of freedom, which is roughly 100. So this is the amount which is true for the standard model. Okay, and I don't think I have time to go into detail here, but I will just state the result. If you take into account this non-equilibrium factor, if you take into account the order of magnitude of this relationship, so this order of magnitude of this relationship is square of Yukawa coupling. Okay, so because this difference will be proportional to Yukawa coupling to the 4th power, and you divide it by the total width, which is Yukawa square, then you find out that you can reach the required baryon asymmetry of the order of 10 to the minus 10 or so, if the mass of these particles is greater than 10 to the 13 GeV. So if the mass is smaller, it doesn't work. Okay, there are some refinements of this number. So the estimate which I was doing was very rude in the sense that I was not taking into account the flavor structure of neutrino masses. So if you take that into account, then this bound is weaker, and you get Mn greater than 10 to the 9 GeV. But still, it indicates that the masses of these particles should be pretty large. Okay, now, if you ask yourself, okay, we take this theory, we adapt all constraints which are coming from neutrino physics, whether we can create a reasonable baryon asymmetry, then the answer is yes. Okay, you can do that. You can satisfy all neutrino constraints. You cannot predict baryon asymmetry here. Why so? Because you still have a number of parameters which are not fixed by neutrino physics. Okay? You don't have CP violating phases. There are 6 CP violating phases here, and all these phases appear in the computation of baryon asymmetry. But scenario is perfectly working. It's viable. No problem. Okay, and the kind of disadvantage, it's not a physics disadvantage of this scenario, this is a human disadvantage of this scenario, is that it can never ever be checked. Because if you have a mass, which is the mass 10 to the 9 GeV, it's unlikely if you can find out this type of particles. Okay, there is no accelerator which you can construct here. Any questions at this stage? Yes. This is a number of massless degrees of freedom. I was noting G star, so G star is the same as an F, so this is a number of massless degrees of freedom. It takes into account the fact that we discussed that when the particles, antiparticles annihilate, they produce entropy, and when you compute the ratio of baryons to number of photons, this factor should be taken into account. Okay, any questions about this mechanism? Okay, if not, I have 3 minutes to tell you about another mechanism. So I won't go into detail. I will just tell you that it works. So you can consider so this is low-scale leptogenesis. Okay, I'll just make a picture here. So this is gamma sceleron over H, and this is gamma n over H. So the low-scale leptogenesis, it corresponds to this picture, that our temperature T star is in this region where sphelerons are not active anymore. Okay, so the baryon asymmetry and lepton asymmetry generation should occur here when our particles, H and Ls, enter into thermal equilibrium. Okay. So you can work out everything and find out that yes, this mechanism is also operative, and it can create the necessary lepton asymmetry. The interesting point about this mechanism is that it works for H and L masses starting from essentially 1 MeV. Okay, so if H and L mass is greater than 1 MeV, you can create baryon asymmetry of the universe. And from human point of view, that's very interesting, because if you have new particles which are can be potentially so light, then we can search for them experimentally. Okay, no way for the previous case, but here this is possible. Okay. And moreover, this can be done, well, literally today with existing experimental facilities. Well, not experimental facilities, but with existing accelerator facilities. So I will show you some picture here, and then maybe I will overpass by a few minutes, and then I will finish.
So
Yes.
I would have thought that you need at least maybe 3, 4, 5 GeV for this mass, because of this the reason you gave earlier, that you want to have enough time for the sphelerons to convert the lepton number into baryon number. So 30 times Mn should be bigger than 130.
No, not necessarily.
So why is that not?
No. You, if you have a mass which is so this temperature here, I was telling you. Okay, so this temperature T double star is 30 times the mass of this guys. Okay, this estimate was very rude, and it was based on the assumption that all Yukawa couplings are of the same order, all masses are of the same order. And if this requirement doesn't follow from anywhere, okay, and so if you take into account the more complicated flavor structure, you will find out that this temperature T double star, where they come into thermal equilibrium, can be in this region even for much lighter particles. Okay. Yeah. So the rate can be actually much larger than I was writing. Okay. So thank you for this question. So this was just for the case when everything was the same. So if I put here the coupling of HNLs to leptons, okay, so this is associated with Yukawa couplings, then there is some region here in which baryon asymmetry cannot be created. So this happens because here in this region, this Yukawa coupling is so big that the system enters in thermal equilibrium, and this is related to Haro equation. And so here it literally doesn't work. There is some bound from below in which neutrino masses cannot be explained. So if you take Yukawa couplings very, very small, then the neutrino masses cannot be so large as they are. Okay, and here there is some region which actually goes up to 100 MeV, which is excluded by different experiments because people were searching for this type of particles in the past. But starting at 100 MeV, there is a domain of parameters where you are in complete accordance with neutrino physics, and in which you can create baryon asymmetry of the universe, and which you can test with experiments. Okay, so the experiments which are essential here are the one which is under consideration at CERN, which is called SHIP, Search for Hidden Particles. Then there is yet another experiment also at CERN, which is NA62, this experiment which is searching for Kp nu decay, and then with some upgrade can be used for search for that. And there is a discussion of yet another experiment which is called Matusla. It's also discussed at CERN, where potentially these particles can be found. Okay, and perhaps the last thing which I would say in favor of this theory is that here we have three particles, okay, three new particles. And in fact, one of them can be a dark matter candidate, and the searches of this dark matter candidate can be done with the help of X-ray telescopes. So that's a very interesting dark matter candidate because it has the following property. Dark matter particle, normally you would say that they're absolutely stable. Okay, that's not necessary, right? It's sufficient that the dark matter particle lives long enough, longer than the time of universe expansion. And so one of this particle, HNL, with the mass of few kilo electron volts, it is a dark matter candidate. Okay, and the way to search is to look for this decay. N is going to neutrino and gamma quanta. Okay, so that's very interesting decay because you look at in the universe, you look at the place where dark matter is situated, and you expect to get a monochromatic flux of gamma quanta coming from this direction. Okay, and these searches are on. They will be done in the future. There were even some indication of 7 keV neutrino here, but this is kind of controversial. The evidence for this neutrino, some people believe that yes, dark matter was discovered. Some people say that no, not at all. So we should wait for a few more years for this question to be settled down. Okay, so I think I stop here, and yeah, that's it. Yeah.
If these heavy neutral leptons in the scenario of low scale leptons, if they start decaying after the sphalerons become inactive, how does it work out?
Yeah, it works out in the following way. During this period, these particles are out of thermal equilibrium. Okay, and so initially, their concentration was equal to 0. Say after inflation, they are not created. The Yukawa couplings are so small that they are literally absent in the plasma. And then during this period, their concentration is growing up because they interact with other particles, and eventually, in this point, they come into thermal equilibrium. But it is essential that here, in this domain, they start to appear, and it's essential that at this time they can produce lepton asymmetry, just because they're out of thermal equilibrium and because the interactions with the rest of the plasma doesn't conserve CP. Okay, so there are all sorts of interactions which they participate in. This is also a quantum system, so these particles are so weakly coupled that they keep their coherence during the evolution of the universe, which enhances CP violating effects. Okay, and so as a result, there is some lepton asymmetry which is generated here during this period, and then it can be transferred into baryon asymmetry due to sphalerons. Okay, and the way to attack this problem, just a few comments. I was talking about thermal leptogenesis. Okay, so what is the machinery there? I was just giving you the order of magnitude estimates, nothing more. But if you want to be serious, what you should do, you should write down kinetic equations for all the particles which are participating in this game. Okay. There are plenty of different particles, plenty of different leptons, Higgs boson, all this stuff. You have to compute all the rate of different reactions, plug it in kinetic equation, and then solve this kinetic equation numerically. Okay, so that's how you proceed in the first case. So the second case is similar, but there are a few new effects which should be taken into account. And this new effect are coherent transitions between different HNLs. And these transitions cannot be described anymore with Boltzmann equation. You have to introduce density matrix, which accounts for that. And then again, you have to look at all the processes. So there were quite a work which has been done here. And this quest, this study, is not completely finished. Okay, so there are several points which people still are clarifying. Okay, but the basic ingredient is that you have non-equilibrium, you have CP violation, so you can produce lepton number. Yeah. Yeah.
So I didn't understand why. I mean, we say that basically to produce this asymmetry, we have to be out of equilibrium in the case of the process with which we compare the rate of the decay of this n particle. Mm-hmm. But still we have to be in equilibrium concerning the Sphaleron rate to convert the. How this? I mean, before we say that basically if we are in equilibrium for the Sphaleron, this can destroy this. This asymmetry. So how this?
Okay. So the so lepton number production. We have lepton number production. And this lepton number production let's consider it for the moment, ignoring sphelerons. Okay. So once you have lepton number production, you create L1, L2, L3. And these are lepton number in first, second, and third generation. Okay. You also once you create L1, L2, L3, in generally you create also N1 plus L2 plus L3, which is the total lepton number. And once you create that, you also create B minus L. Right? Because B is not participating here. You create L, you create B minus L. Once you create B minus L, you cannot change that by sphelerons.
You cannot.
You cannot.
Yeah.
And once you created that, you are guaranteed that you produce baryon asymmetry. So here, the important point is that in this model, the quantum numbers which were conserved in electroweak theory, B minus L, is not conserved anymore.
They don't cancel each
Yeah.
other.
Yeah.
So what's the mechanism that sets the radical abundance of the mathematical candidate?
Yes. This is I erased. Okay. The mechanism is just normal weak reaction. So you have, for instance, lepton, anti-lepton, Z, neutrino, anti-neutrino, and here you have N. Okay, so there are this type of reaction, and this is the Higgs field. You have collision of lepton anti-lepton that would produce neutrino anti-neutrino, but there is mixing between neutrino and this particle, so this type of reactions produce dark matter particles. Okay.
So it's like a Frisin, or?
Sorry?
It's like a Frisin, or?
No, it's not the freeze in and freeze out. This is just continuous production. So this, people talk about thermal relic for dark matter particles. And then they have in mind freeze out. So for WIMPs, for instance, and other particles, the scenario is the following. These particles are in thermal equilibrium, and then at some stage they go out of thermal equilibrium because they annihilate with each other, okay, and this freezes at some stage. So here the situation is different. So these guys are never ever in thermal equilibrium. Okay, you start from a zero, and then this type of process just continuously create the concentration. This process is away from thermal equilibrium, but you still compute a number of particles.
So there is the assumption behind that
there is, yeah. So for this type of assumption is realized, for instance, in Higgs inflation. So you have the standard model, Higgs boson decays, and then it doesn't produce any of HNLs. Okay, so it's not that simple as I wrote here. Okay, you have to work out many different things. You have to work out that the neutrinos which appear in here are actually propagating not in vacuum but in the medium. This leads to a modification of many cross sections, leads to quite a number of unusual results, to possible enhancement of production in some particular cases. And this is also quite an active area of research. But it's more or less settled down in the sense that we understand this process pretty well.
Okay. One question. Yeah.
How important would you rank naturalness problems? Because you had this remark that this model more or less solves the big problems.
Well, there are several naturalness problems which we can address here. Okay. This model is as natural as the standard model. Okay, not worse, not better.
No, because many people consider the naturalness problems that are present already in the standard model also as motivation for extending it.
I'm not in this camp. Okay. Yeah, I can elaborate on this point. Yeah, if you just take the standard model as it is without gravity, then this model has just one mass scale. Okay, it's just the mass of the Higgs boson, and as such, this model is natural. It has just one scale. There is nothing to compare it the scale. Sometimes people talk about quadratic divergences, cutoff, but this is purely mathematical procedure. The existence of this cutoff, it can be evaded, use another regularization. Anyway, this is an intermediate thing which is introduced in computations. So the standard model as it is, if you forget about gravity, is to my taste, it's natural theory. This theory, it has several mass scales. It has the mass scale, which is associated with the Higgs mass, and then the mass scale which is associated with right-handed neutrinos. If right-handed neutrino mass is very large, 10 to the 13 GeV, then this model has naturalness issues, because you can take the Higgs, then here you have n particle, here you have some lepton, here the Higgs again. You can compute contribution of these graphs to the Higgs mass, and you find out that this contribution may be large if the mass of n particles is large. Okay. This contribution is comparable with the mass of the Higgs boson if the mass of n is smaller than 10 to the 8 GeV. So if mass is smaller than 10 GeV, there are no naturalness issues in this theory as well. Okay. There may be a tension with thermal leptogenesis of this constraint, but okay, who cares? Of course, the standard model and this theory, they are not alone, because there is at least gravity involved. Okay, and the gravity seemingly introduces yet another scale, which is the Planck mass. Okay. However, the Planck mass, as it stands in the action, is not the mass of any particle. It's a strength of interaction. It's a strength of gravitational interaction. So the new particle which is associated with gravity is graviton, which is perfectly massless. And so it's not legitimate, I would say, to compare the Planck mass, which is not a mass, which is a coupling, with the mass of the Higgs boson, which is a mass of some particle. Okay, and so whether the presence of gravity induces some naturalness issue or not is an open question, at least to me. Okay, so for instance, if you use dimensional regularization and compute radiative correction to the Higgs mass in Dirac, you will find out that they're all suppressed by the Planck scale. Okay, so they're small. If you cut off regularization, then you can get different answer. But at least there is a way of treating this theory in perturbation theory. That, but I mean, in order to really know whether this is a problem or not, you should go much further. You should be able to understand what the gravity is, how to deal with the gravity and the strong coupling, and that we don't have at hand yet.
And this idea that the lightest black hole should start at masses of order of Planck mass?
Yeah.
Effectively constitute also states with mass and Planck in height. Yeah.
Yeah, I mean, so different people have different approaches. If we talk about, for instance, we can take Diet-Wally, who likes the idea that the gravity is a theory which self-completes itself. Okay, that's one approach in which you don't need any new physics whatsoever. The presence of black holes make the UV behavior of gravity to be perfect, and the hierarchy problem doesn't appear, that's it, okay? There is another line of thought which is related to asymptotic safety, which says that also gravity is self-complete, but there is some non-trivial UV fixed point corresponding to gravity, but you don't need anything else, and there also this hierarchy problem appears in a completely different way. So for me, it's kind of there are no certain yes or no. Okay, there are things to explore.
Okay, this discussion is obviously very interesting, but maybe it can be continued over a cup of coffee. So let's thank you again for the next.